So welcome everyone to the FRET in MetaMorph webinar. So what we'll be covering this morning is looking at, kind of do a general overview of FRET within MetaMorph. We'll look at the experimental design. We'll look at the dialog boxes that are in the software. We'll talk about the correction factor calculations, and we'll kind of go over a little bit about how to calculate some FRET efficiency. The goals for this webinar will be just to get you familiar with the tools that are available within MetaMorph to do FRET analysis. We'll provide a basic understanding for each tool's use, but we won't necessarily go over every button or setting within all these functions that we have. Just some generalized information. The PowerPoint, along with the presentation video recording, we'll make available to you. So you'll have this information, but if you need to get in contact with us for some help, questions, and so forth, you have the 800 number listed there that can be used. This gets you through the phone tree to get to our MetaMorph support. Also, our email address, support.dtn@moldev.com, and then the website is support.meta.moleculardevices.com. There's a whole host of things available on our website, from what hardware we support to what operating system you can use, what version of the product, and along with a bunch of application and technical notes that will be available on our website as well. So just for a generalized overview of FRET, just to get an idea, what we're looking at is a Jablonski diagram of the forcer's resonant energy transfer. So we can see on the donor side, we excite the donor with a specific emission excitation wavelength. The molecules get excited, and there's several different paths that it can go through in order to return back down to the ground state. The most common path that most people will see will be the actual emission of a photon, and then it will return back down to the ground state. That's represented by the solid color here. Another potential path that the energy can be degraded back down to ground state is to pass that energy on to an acceptor and excite the acceptor, and then the acceptor can give off a photon and return back down to ground state. And this is the concept of what resonant energy transfer is all about. And FRET does require fluorophores with an overlap of spectra. You have a donor excitation, and the acceptor emission is what you're looking for. So the blue line here represents, in this case, it's beryllium CFP spectra with the YFP emission or excitation spectra. So we see the emission spectra of the CFP along with the excitation spectra of the YFP, and it's this area that you're looking for significant overlap between the two fluorophores that enable FRET to happen. There are several factors that actually affect FRET measurements, and so we'll work through these one at a time and also look at ways that we can kind of overcome some of these factors. So the first is you have donor acceptor fluorophores might exhibit significantly different brightness levels when imaged together. So what this really means is that your donor fluorophore may actually either be brighter or weaker than your acceptor fluorophore, so you need to look at ways of trying to balance that out. For one way to overcome that would be fluorophore selection, so you need to look at the fluorophores you're dealing with and see if there's some better ones out there that are more balanced as far as the relative brightness. The other is to optimize acquisition parameters, so you can specifically adjust your acquisition parameters to get more of a balanced intensity between the two fluorophores. And additionally, one thing you can't stress enough is you always want to make sure, specifically when you're dealing with fluorescence, but even more so when you're dealing with image-based FRET calculations, is you need to make sure you're doing proper imaging techniques. That means you're coloring the scope, so make sure the scope is properly aligned for the light. You also want to do background subtraction, either at acquisition or post-acquisition. And I'll show you how you can do a post-acquisition within the software. But you should always do background subtraction, which is eliminating the noise component of the signal that you're looking at. The other factor that can affect FRET is your donor to acceptor stoichiometry that lies outside the ranges of 10 to 1 or 1 to 10. What that means is that if those ratios are beyond those levels, you're going to get some either false positives or potential false negatives based on that ratio. So you always want to try to balance the overall acceptor and donor expression levels that you can. So ways to overcome that would be optimize your experimental design and cell loading. You have alignment orientations of the fluorophores in order to get proper FRET. One, the fluorophores have to be fairly close together, and the other is because it is a polar molecule that do need to be in a specific alignment. And unfortunately, there's really nothing you can do regarding that. So it's based on just how many molecules you have that are close together and whether it will happen or not. The other issues that affect FRET is bleed-through, or in terms of crosstalk or crossover. And what you're dealing with is cross-excitation between spectrally overlapping fluorophores. So that's one of the things that happens. And the correction for this is found in the formulas that we have for correcting for FRET. So what we're looking at as far as when we're talking about the crosstalk is the amount of bleed-through that you get. And this is specific to the filter sets that you have. And there are correction factors in the formulas in order to remove this bleed-through. So what we're looking at here in the excitation crosstalk is basically because of the YFP has such a long excitation tail here that goes into the excitation spectra of the CFP. What we're looking at in this case is the amount of direct excitation from the CFP excitation light that will excite the YFP directly. So in this case, this is the amount of fluorescence that you'll be detecting and recognizing when there's really no FRET going on. So you need to subtract that out of the overall information that you're getting. And then the emission crosstalk is the amount of, again, we have a fairly large tail on our CFP, so this is the amount of CFP emission that can be directly detected in the YFP emission channel when we're dealing with the fluorescence. So this is just how much of the fluorescence we're detecting on our YFP signal that is basically just CFP fluorescence directly. So it's so both of these factors need to be accounted for and removed from the overall results to get your corrected FRET calculation. We'll work through just kind of a typical FRET experiment and see kind of how things could be set up for that. So first off is you need specific filter sets in order to do FRET. You'll start with a donor filter set, which would be, in our specific example, we're doing CFP and YFP. So donor filter set is a CFP excitation with a CFP emission. The acceptor filter set will be a YFP excitation with YFP emission. And your FRET filter set will be a CFP excitation with a YFP emission. So those are the three combinations. Typically, you'll use a filter wheel because that's the best and most efficient way of generating that. Because if you use three separate filter cubes in a turret setup, you can potentially have some alignment issues because of the fact you're changing mirrors around to get the three combinations. Sample cells that you'll be using, you need to have a set of cells that only have the donor loaded into it. So CFP tag compounds are loaded into it, so your donor-only sample. You need an acceptor-only sample, so these are just YFP tag compounds. And you need a FRET sample, which have cells labeled with both CFP tagged and YFP tagged components. A typical experiment will include several different slides. So you have one slide of a donor-only sample. You have one slide of an acceptor-only sample. And then you should always also include a negative control. So this will be a control sample that you have that you know that no FRET will be going on, interacting between those two compounds. And then you should include a positive control, so it basically it's the two CFP and YFP with a small linker between that are close together that you'll get FRET most of the time. And then you want several slides of your experiment set that you're trying to measure. So looking at the corrective fret formulas and what images you need to collect within MetaMorph to do the analysis. So we're going to talk about, one of the things we're not going to get into is discussion of which is the best method in order to do fret. That's one of those things that we provide the tools that enable you to do it. It's going to be up to you to decide which method that you want to do based on the research that you've done through the publications. And so the first method that we have available is called Sensitized Emission. And this requires 7 images in order to perform the sensitized emission calculations. And the way to read this graph is that the samples, as far as the cells, are located on the left-hand side here per row, and then per column is the actual filter set you're going to be using to do that acquisition. So you'll need 7 images, and the 7 images that you need are as such. To calculate the coefficient A, which is this calculation here, is a factor of the acceptor image that you're dealing with that's going to be subtracted out. So this will correct for any crosstalk that you get from the acceptor side. And this is going to account for any crosstalk that you get from the donor side. You're subtracting both of those out of the raw fret image to end up with a corrected fret image. So to calculate the coefficient A, is simply the acceptor-only sample. So it's an acceptor-only sample in the fret filter set. So we're doing CFP excitation with YFP emission, and we're dividing that by the acceptor-only sample that's in the acceptor filter set. So that's your denominator here. So it's taking values from this image divided by values from this image and doing the calculations there. Coefficient B is your donor-only sample, so only CFP, and it is taking the values from the fret image filter set divided by values from the donor filter set is what you end up with, those calculations. So you end up with a raw fret minus the cofactor, a coefficient value you have here, times the acceptor image, which is this image here. And then it's also minus the cofactor from this arithmetic times the donor image to end up with a corrected fret. So 7 images you need in order to do sensitized emission. You need a you need a donor image, an acceptor image, and a raw fret image. And those are with the cells that are loaded with both CFP and YFP imaged in the donor filter set, the acceptor filter set, and the fret filter set. And you need these other 4 images to do the coefficient calculations. The specified bleed-through, this is doing more correction, and you need 9 images, so you need basically every image that's in this grid in order to do this calculation. You have the following calculations for that. I'm sorry, I'm just reading some of the questions that just... So, Brian Snyder asked, how do you address bleed-through with intermolecular fret experiments such as chameleon? I don't quite fully understand what you mean by how that differs from what we've talked about with just the two fluorophores. And can you talk about antibody fret setup? The purpose of this webinar is to look at the tools that are available within MetaMorph to do the analysis. I'm not really going to go into much more detail than what I have as far as the overall experimental setup. These are things that you'll have to kind of work through based on the literature that you're looking at. Okay, so specified bleed-through, 9 images, several more corrections, so the formula is a little more complicated than what we're dealing with. So there's a lot more subtraction going out to account for some of the crosstalk, or more of the crosstalk that's associated with the filter sets that you deal with. So again, we look at the donor and acceptor. So this is how much of the donor is coming through in the acceptor channel. We look at the acceptor-only sample in the donor filter set, and then divided by the acceptor-only sample in the acceptor filter set to get that calculation. And then we look at the acceptor and donor. So this is the donor-only sample in the acceptor filter set divided by the donor-only sample in the donor filter set. Then we look at donor fret and acceptor and fret to do those same calculations. And we see the overall formula listed here. Okay, looking at what the fret dialog looks like within the software. So under the apps menu is where you'll find the fret dialog, and the first thing we're looking at is through the Sensitized Emission. So the initial setup tab, you'll typically set as far as the source to be the components, or do Sensitized Emission. We can see the overall formula listed here. Then we'll select our donor image, which is the fret cells with the that were imaged with the donor CFP filter set. The acceptor image, which is the fret cells that were imaged within the YFP filter set. And then the raw fret is the fret cells that are imaged with CFP excitation, YFP emission. So those are the 3 images you select here. We'll work through how to calculate the constants that you'll enter here. And then additionally, if you need to do some background subtraction on the images first, you can do that within the dialog as well. Once you have 3 images selected and the appropriate constants calculated, you can click apply, and it'll generate a corrected image for you. The specified bleed through, again, same 3 components as far as the donor, acceptor, and raw fret images, but you end up with potentially 4 more cofactors that you're doing the correction within that, and you run through the same formula to do the corrections for that. And what I want to show you is actually within MetaMorph how to do some background subtraction to correct your images, and then how to work through the coefficient calculations, and then additionally how to generate the fret images. Okay, so if I open those aren't the ones I wanted. Okay, we'll look at our CFP images first. Okay, so the initial images that we're dealing with are coefficients. So this is the CFP-only sample that was imaged with the CFP excitation, CFP emission. This is CFP-only sample that was imaged with the CFP excitation and YFP emission FRET combinations. So these are the raw images that were acquired, and we're looking at the background subtracted images here. And I'll show you additionally why it's important to do background subtraction, because how that will adversely affect the overall coefficient calculations if you don't do it. So in order to do background subtraction, so we'll simply close these images and we'll work through the background subtraction process. Go to the process menu and open up background and shading correction within this dialog. So the first image that we're going to deal with, we'll start with the CFP here, is we're going to do statistical correction, which is basically taking, in this case, we're going to look at the average intensity value within the image. We want to create a region of interest on the image that's in the background area, more or less where there are no cells. And we'll use that, and we'll also want to use the same area between both images in this case. So we'll copy the region. That's simply a right mouse click inside the region. Select copy region. If you right mouse click again on the new image, select paste region, you're pasting the region in both the same location in both images. So if we start with the CFP image, we're doing a statistical correction, average intensity value within region number 1, and click apply. This is the background image that we deal with. If we do the same thing for the FRET image, in this case CFP sample with the FRET filter set, and click apply, and this is the background subtraction that we deal with. So in order to calculate the cofactors, it's simply, in this case, it is the amount of fluorescence that we see in this image divided by the amount of fluorescence that we see in this image. So we can place a region on our sample, and again, we'll put them on the same spot on all the images. And if we measure the average intensity within each of these images and log them out to Excel, we end up with something along this line that we see here. So this is basically looking at from the background subtracted images, we end up with a certain value, and the ratios that we end up with, the average between those happens to be about 0.5938. Now, what I wanted to point out is the fact that in this example, this was with the YFP images, is the difference between background subtracted versus not subtracting the background. So we came in and measured the average intensity within the YFP channel, the YFP cells on the FRET channel and the YFP channel, and we see fairly significant differences in the fact that that ratio ends up with being about a 0.3, a 0.49, so we end up about a 0.4 for the background subtracted images. But if we look at the uncorrected or not background subtracted images, we end up with now a cofactor of 1.3. So now we're going to be definitely over correcting in this case. We're subtracting out more of the fluorescence than what we will in this. So will adversely affect the overall results. So that's why it's pretty important to do your background subtraction to guarantee that what you're looking at is true signal and not signal plus noise. So we end up, in this case, for our coefficient A for our calculation for sensitized emission is 0.4, and our coefficient B, in this case, is 0.593. We'll just stick with that. So
It looks like
Yes.
There are four questions currently in the Q&A. I don't know if you want to take a look at a couple of them that deal specifically with what you're doing right now.
Is there a significant instance where one method is better than the other in subtracting? This is Wallace. I'm assuming you're referring to the background subtraction or correction. Looking at the dialog itself, the subtract background there's methods within that. What you're doing, you either subtract a constant value, which typically is you look at the average intensity of the background area and you just subtract that. The background image, so you've acquired an image to generate the background that's there. So this will work. I typically would prefer to do the statistical correction in the sense of using a region, because that would take into account if there's any autofluorescence that's associated with the media or some other compounds that are within the sample. It'll correct for that as well. So for me, I would probably work off of the statistical correction methodology. The correct shading is designed to balance for uneven illumination across the field, so you don't necessarily need to do that for background subtraction. And then the flattened background is also the same thing. You're trying to produce a background image by doing some processing that will smooth the entire image, and then you'll subtract that from the original result. So for doing simple background subtraction, it's either subtract background, which works off an image or a constant value, or the statistical correction, which is taking the average min or max from a region and doing that subtraction. For these cases, I would necessarily prefer probably doing just a statistical correction. Okay. Try to get back to Brian's question. We're looking at the intermolecular fret that has both CFP and YFP expressed in the same molecule. And it says to do these bleed-through calculations with CP only and YFP sample only, you're suggesting the research must express these molecules separately. In order to do these calculations, you do need a CFP only sample and a YFP only sample. There are several other ways of calculating fret, except for photo bleaching is one, that you don't need to do the bleed-through calculations for that. So in this case, if you only have the one sample to deal with, you won't be able to correctly do the fret calculations through the specified bleed-through or the sensitized emission. So, like I said, there are several other methods for doing that. And also because there is still a lot of discussion going on about fret, my understanding is a lot of the reviewers for most of the papers out there do require more than one method of doing your fret calculation. So, except for photo bleaching is one method that people do for them because it's very quick and easy to work with. Okay, so Sung Hein Chen, I think as far as the background is uneven, how do you deal with that for correction? That's your correct shading calculation, so you will need a background image and a shading correction image. The background image is typically acquired with no light going to the sample, so you're subtracting out any electronic noise. Shading images, you'll either need a shading slide. In essence, Chroma sells these colored slides that you can use for fluorescence that work pretty well of looking at shading across the image. So if you have uneven illumination, hopefully it can be also fixed by setting up the microscope correctly. Okay, looking at Wallace's question about one method over the other, sensitized emission versus specified bleed through. Is one better than the other? I can't really comment on that. Again, that's stuff that's in the discussion in the literature about one method versus the other. Our job here is to provide you the tools to do the analysis the way that you want to. And so we provide both options available to you. Okay. So we've done our background subtraction. We've seen the importance of doing background subtraction. So now let's come in and actually look at what a corrected fret will generate for us. Okay, so this is our double-labeled sample that is expressing fret. So we have the CFP and YFP samples that have been imaged with just the YFP filter set, with the CFP filter set, and with the fret filter set that's here. So if we go to the apps menu and look at fret, so our donor image is the CFP image. Our acceptor image is the YFP, and then our fret image is the fret that's here. Okay, so those are the three selections we're doing sensitized emission. Okay. In this case, these are the raw images. I haven't done any correction for them, background subtraction for them. So I want to do that within the dialog, and it places a region of interest on the image for me that I can move around. And notice when I move one, it moves them in all three images. So the regions are linked, so you're subtracting, in this case, it's the average intensity within the region. You're subtracting that out before it does the calculations. The constant A and constant B are the values that I got from my spreadsheet. So that's this value for constant A, which is from the YFP images, and this value for constant B, which is from the CFP images that we acquired. And so those are the constant values that I placed in here based on the initial setup, and then when I click apply, this is the result that I get. So if you want to see the difference between not doing background subtraction versus doing background subtraction, you can definitely see how more of the background is being subtracted out of the image in this case here. So what we're looking at is truly corrected fret. Okay. So that's with a set of cells that is expressing fret. If you want to see what it looks like with cells that are not, we go back into our mutant samples here, which means they are not expressing fret. So this is our YFP, CFP, and fret image cells. We use the same constant values because these constants are calculated based on the filter set. So as long as we don't change our filters, we can pretty much use the same constants within the calculations. I would typically recommend doing the constant calculations, so doing the CFP only sample, YFP only sample, pretty much through every set of experiments that you're doing. That way, if the imaging parameters change slightly, you may get some slightly different values here, and you'll correct for that as well. Okay, so our donor is our mutant CFP, our acceptor is our mutant YFP, and then the mutant fret is what we end up with. In this case, we're not doing background subtraction because to show you what it really looks like. So you can definitely see from original where the cells were expressing, you thought you were getting some fret because you got some signal listed here, But after doing the correction calculation, you can really see the fact that this is a lot darker here, so we're not seeing any expression. And again, if we do background region on this, click apply, you can definitely see where the cells were expressing signal, you have no fret going on there. So the images that you're generating from these formulas is corrected fret, so they're intensity images. It is not any efficiency calculations, and again, this is another, I wouldn't say controversy is kind of a strong term, but there's a lot of discussion on how to calculate fret efficiency. So you'll need to do the research within the papers to figure out the best technique or method in order to do fret efficiency. Some will take the image, the corrected image, divide by either the acceptor image, this one, or by the donor image, this one. So it really depends on what method you want to use in order to do that fret efficiency calculation. And I can kind of show you within MetaMorph one method, which will take the fret corrected image, which in the case will be this image here, and if you divide it by, in this case we'll divide it by the acceptor, so it's the corrected fret divided by the acceptor in order to get a efficiency calculation. You can do that under process, arithmetic, and simple image arithmetic. So the source one is going to be our corrected fret image, which is Untitled 2. And then our source 2 is going to be the double labeled YFP in this case. So it's corrected fret divided by acceptor image. In this case, I'm dealing with 16-bit images, so my results I want to be 16-bit. I'm going to do a divide, and because of the fact that MetaMorph images are integers, not floating point values, you're going to need to add back some or do a multiplier to get values that represent, in this case, percentages. So by doing a multiplication of 1,000, when I measure intensity values, it's going to be expressed as a percent. So I click apply. Turn off auto scale and scale this up so you can see really where, so you can definitely see the fact that fret efficiency is typically anywhere from 20 to 40% is very high fret efficiency. So if I now come in and create a couple regions of interest on this result, and then go to measure region measurements, and we'll look at all regions and look at the average intensity. If I move the decimal place point over one value, so in this case, the way to interpret these results is that I'm looking at a 37.5% fret efficiency, 29.4, 36.8, 34.3, 30.2. If I look at the average intensity within this, so that's a 33.6% average fret efficiency calculations. So hopefully everybody can see the fact that by doing the arithmetic, so the corrected fret divided by, in this case, just the acceptor to generate the fret efficiency, but I have to do the multiplication by 1,000 to generate these numbers, and then it's just a matter of moving the decimal place over, so I have 1 decimal point percent ranges for that. So we can see we're falling within what the expected efficiency rating should be within a typical fret experiment, somewhere around 30 is a good expression. Okay. So that's all I have within this. We do have a technical note on our website which kind of walks through as far as what images to take, typical experiment setup, as well as how to do this fret efficiency calculation. Again, like I said before, our job is not, as far as being a software manufacturer, we're not entering into the discussion on what are the best methods to utilize. We provide you the tools to do those calculations that you need. And so if you have specific questions about the tools available, I'll be more than willing to entertain those. Additionally, also, as it comes along, you can also send any questions you have to support.dtn@moldev.com is the typical support email address to get a hold of us, and we'll definitely help you work through this process.
There are 4 questions in the queue.
Okay. Okay. The first question about using the raw image. Basically, I was just working off of the not background subtracted. This is the background subtracted, so we could have worked off of. And so look at the results. So if I change those values to, again, turn off auto scale. Let's scale this back up again. Just transfer the regions from so in the same spot. And so in this case, you can see then the background subtraction does significantly change the overall result. So again, that's the other potential controversy dealing with image-based Okay. So we can see we're dealing with a 13, a 9, 11, 12, a 7, a 5%. So our average is right around 9% efficiency. So again, why it's important to utilize background subtraction that can potentially give you some false positives.
There's a question earlier from Guillermo about is there a way that upon setting the regions, MetaMorph can automatically calculate the constants?
No. Right now we don't have that built into the dialog, so there's really no way of doing the auto calculations for the constant.
Also, Alfred Hernandez asked, is fret supposed to be seen as bright dots in the corrected image?
In the corrected image, yeah, as far as the brighter the intensity that you have, the more fret that's going on. But again, that's just a qualitative value for the correction. In order to really know how much fret you have going on, you need to calculate the fret efficiency, because the other purpose for that is from the fret efficiency, you can actually calculate the intermolecular distance between the two molecules. And so that's the whole purpose of getting to a efficiency value, is to look at that.
Songhai, again, do you need to do background correction for both corrected fret and YFP images before calculating the ratio, and how do you export the images with the scale bar?
This is a scale bar as far as intensity, or scale bar as far as size, I guess that's the two different.
She does not specify.
Okay. So scale bar within intensity can be done through under the display menu, graphics. Actually, you would draw a gray wedge on the image for that. You would specify the range between those. So that's how you would set up the intensity scale bar within the image.
And also, do you need to do background correction for both the corrected fret and YFP images before calculating the ratio?
You should always do background subtraction before. Again, because that way what you're looking at is true signal. So in this case, because I think that's also, this result is probably a bit skewed in the sense that this is an uncorrected image. I should have done background subtraction on this and divided it by this image. This also explains why I matched the uncorrected versus the not background subtracted initially. So my fret efficiencies were probably a little low here because these background here is a lot higher than what it is here, and so that division is going to be a little bit larger. So
Alfred Hernandez has a question about, will MetaMorph capture the images for us, and where do we specify the order we want them to be acquired?
Okay, MetaMorph, can capture, there's a variety of different ways of doing that. You can do simple acquire. So you specify, in this case, you set up the wavelengths that you're wanting to do, whether it's CFP, YFP, and fret is the illumination setting that you'll use. You select CFP, do the acquire, select YFP, do the acquire, select fret, and do the acquire, so you're manually collecting those. We also have, under the apps menu, a multi-dimensional acquisition, which will acquire all three wavelengths not simultaneous, but in sequence for you and allow you to utilize those images. Additionally, we also have acquire multiple wavelengths, which allows you to do your three wavelengths at that point. And then you can specify the exposure times that you want to utilize, and then you can acquire all three wavelengths at that point. So there's a variety of different ways of doing that. The sequence is totally up to you because, again, within the fret dialog, you're specifying the donor, acceptor, and fret image for that. So.
Well, that appears to be all the questions for right now. Does anyone else have any questions for Ed? Oh, yes, Brian Schneider. Is there a simple way to do ping pong fret? DFA-AFD instead of DFA-DFA?
To be honest with you, I've never heard of ping pong fret, and so I don't have an answer for that.
Well, it doesn't look like anything else right now. Again, like Ed said, the questions can also be forwarded to support.dtn@moldev.com if you have any further questions. Also, please remember that this webinar will be posted. Oh, we have one more question.
Yeah, one more. From Alfredo, is fret occurring all the time or just when we excite the donor? Again, you can potentially get some fret through, as far as the only true way fret is happening is if you excite the donor, because that's the true calculations. The potential problem that we see with both the emission crosstalk and the excitation crosstalk can happen, and why they need to be corrected. And so that's what get back to my PowerPoint and kind of show you, again, that slide. So what we're correcting for is this is the direct excitation of the YFP fluorophore from the CFP excitation. And then this is how much of the CFP emission is bleeding through the YFP channel within that. So we need to correct for both of those to look at what our true FRET signal is. Okay, I think that's all I got for now. So,
again, this is being recorded and will be posted on our moleculardevices.com website. If you have any questions, again, just let us know at support.dtn@moldev.com. Thank you all for attending, and thank you for being patient with us in our first webinar. And good day.